So welcome back, everybody. And this is our last session. And what I wanted to do today was more to wrap up the things we discussed yesterday. And I wanted to point to that pairing model code, which could be useful for the final presentation. Then I'm going to use slides because I have slides on singles and doubles. And they will also serve as a way to repeat what we have done during the semester. So the different elements today will also contain some reminders and pointing to things which we have discussed earlier this semester. So I wanted just to bring back a little bit of the things we did yesterday with the diagrammatic representation. And this is something which we can wrap up in a very nice way and then write down the diagrams. And with the diagrams, we can then, with the diagram rules, we can then actually set up the analytical expressions which need to be coded. I'm going to remind you of the diagram rules when we also look at the singles and doubles excitations, which is a kind of not exactly golden standard when you do couple cluster theory, but it's the starting point for basically all the standard approximations. So what I want to do now is just quickly switch back to the whiteboard, and then we are going to look at some of the equations, and then I will go back to the Jupyter notebook and discuss the code, and then also discuss singles and doubles excitations. And that's basically going to be the end of the semester, or the last topic which we cover this semester. So let's go back to the whiteboard and wrap up a little bit the things we did yesterday. So yesterday what we had, and let me just move this one so I have it down here. So what we had yesterday was what we ended yesterday was a diagrammatic representation of the equations. So for the CCD equations, what we ended up with is, in practice, we end up with an equation for the energy where we multiply with phi 0. We have E of T2 multiplied with phi 0, and this is going to be equal to, and we found that this was equal to the ECCD times ET2. When we expanded that one, there was only one possibility, and that was the one which contains the first term. Then we had the other equation, which gave us the equation for the amplitudes, and we had this term AB, and then we had H of ET2 of phi 0, and then we got that this one is equal to the ECs, or let's just put it ECCD, which is just a constant multiplied with the state phi ij AB, and then we had ET2 multiplied with phi 0. And when we wrote that one out, we got an equation which here was equal to ECCD times the amplitudes, the unknown amplitudes. And then we would shuffle that to the other side, and we could write something in terms of the so-called correlation energy. Now, what we did yesterday was to then write the operators, the one-body and the two-body operators in terms of excitation levels. So what we had then was a operator Fn, which we diagrammatically simply wrote in terms of excitation levels. So we call this level +1. So we have created a one particle, one hole state. Here we destroy a one particle, one hole state. And we call this for level -1. And then we had these ones, and this one, which is a whole state, which goes through the diagram, or particle state. And these two have no particle whole state, so we call that a level 0. Then we looked at the two-body operator. So I'm just reminding you of some of the things we did yesterday. So with a two-body operator, we would have a series of diagrams, which then represent different excitation levels. And I'm just going to list them again. So this is level 0. It's just a 2-particle diagram. We have a diagram here, which I write without adding the exchange term. So this is a whole state. So these are all level 0 diagrams because I don't create a particle whole pair. So these diagrams would be diagrams which we call level 0. And then we could have diagrams of this type. So where we have, this is the 2-body operator. So this will be a level 1. So I create a 1-particle, 1-hole pair. Here I destroy one. So this is -1. And then I would have a similar one for the whole states going down here. So I can have a level 1 here. And then I would have a similar one here for the whole state, which is a -1. And then we have the diagrams of this type, which is a -2. We destroy a 2-particle, 2-hole state. And then finally, we have the one here where we create a, sorry, not that way. And this is a level +2. And then in our case, we have the T2 operator, which is just given by this diagram here. And this is a level 2. So when we look back at the equations, what we have then, when we are going to match these different terms, is that in this term here, we're actually going from a 0-particle, 0-hole to a 0-particle, 0-hole. So if we think of terms of excitation levels, this is just a 0 level. And that means that what comes in here has to match a 0-particle, 0-hole state. Whereas in this case, we actually end up with a term where we start with a 0-particle, 0-hole, a level 0, and then the operator does something, and we have to end with a 2-particle, 2-hole state. So what we can do then, when we look at a diagrammatic expansion, we can simply try to match these different terms. And what we found yesterday is that we had the following diagrams. So we have for the energy, this is the energy term. That's the first equation which we looked at. This is the correlation energy, delta E at the CCD level. This was given by this diagram. That's the only diagram we have. And then we have an A and a B, an I and J. And when we use the diagram rules, this can be written out as a 1 divided by 4. We sum over all the intermediate states. And we have an unknown amplitude, T, A, J, A, B. And then we have an interacting element, an interaction piece, which is given by this one. And I'm skipping the anti-symmetrization side. And the Tij AB is actually given by this term here. So we can use the diagram rules to actually set up the equations by if we have the diagrams. So we would draw all topologically distinct diagrams. Then we had the term which we label as an L1, which comes from the second equation, where we connect with a 2-particle, 2-hole state. And in that case, we would have these diagrams. So we have a 2-particle, 2-hole state leaving. But we can actually attach to this a 1-body operator, which is this one. So here we will put labels. We would have an a state B, state C, and then we have I and J here. And then we had, in addition, another term. So when we draw the diagrams, we draw only the topologically distinct ones. But when we are setting up the equations, we have to take into account that we can actually interchange these pairs here. And that gives a permutation factor, which we need to account for. And you will see that in the equations which we are going to set up at the end. But diagrammatically, this is what we would have then. So we have the 1-body term, which is attached to either a particle line or a whole line. So we have an A, and then we have a B, and then we have a J, and we have a state K here. So that's one of the terms which we then can deduce the analytical expression from. Then we had for the 2-particle, 2-hole guys, what we would have then would be this term which we call L2 here. And then we have a term which goes like this. So we can have a two-hole intermediate state. So we have our A and B, our I and J, and then we have the K and L. We have in addition a new diagram, which is given by the two-hole lines coming in. We have an I and J. We have the particle states A and B, but then we have an intermediate state here, which is a two-particle state with C and D. And then we can set up the different diagram rules to find the analytical expression for that diagram. Then there is a final one, which is now a particle hole excitation as an intermediate state here. And then we have this one, and then we have that. So you see that in all these cases, what we end up with is a two-particle, two-hole state as wanted. And in this case, we have a C, and we would have a K here. Then finally, there is an additional term. Actually, we have several diagrams in that case. So the L3, as we call them. So it's going to be a term which looks like this. Let's see if I can draw them correctly. Because then we had two T2s. So this is the one which comes from the term with the Hamiltonian h of n of T2 squared. So that means that we have two T2 operators at the beginning here. And you see that these are terms which are much more complicated to get in many-body perturbation theory. They would appear in many-body perturbation theory as an intermediate state. However, you see now that if we now are going to look at a contribution to the energy, then we would then contract this term with something which looks like this, because then we go to a zero level state. And then we would link these two with a two-body interaction. And that would give a final contribution to the energy, which, if this is given by a first-order contribution, it will be a diagram to fourfold perturbation theory. So you see now that the equations themselves, they produce much higher terms than you get in many-body perturbation theory, order by order. So if I were to stop at third-order interaction, then I would have gotten this term, because I would match this one with, so if you now think of the energy, you can match all these terms with a two-body interaction here. So what you would have then would be phi 0 multiplied with h, and then with this wave operator. This is a wave operator. This is not a contribution to the energy, but it's a contribution to the wave operator, because we create a two-particle, two-hole intermediate state, which then has to be matched at the end with the energy. So think back to what we did with perturbation theory. In perturbation theory, we had phi 0, and then we had the Hamiltonian h of I, the interaction piece, and that was multiplied with this chain of operators, which was given by the wave operator. So what you're producing here with copper cluster theory iteratively is an updated improvement of the wave operator itself. So if you look at this term here, and you match this one with a two-body interaction to get a contribution to the energy, then this term would be at least third order in many-body perturbation theory. The same with this one, and the same with that one. But when you now solve the equations iteratively, since the equations are non-linear in these unknown coefficients, that means that you will keep piling up more and more complicated terms here. So that means that you see now that copper cluster theory, in principle, due to the fact that it has this non-linear set of equations, produces many-body perturbation theory to infinite order, but a selected class of contributions, because you have limited yourself here to only T2 excitations. So that means that it's only this type of excitations, or these ones, which will happen. Now, to this order, to this L3, there are actually three more diagrams, and they look uglier and uglier. So let me see if I can draw that correctly here. So we have the wave operator, and we have the wave operator here. We have a whole state coming in here. And then we have a particle state leaving like this. So this is an interaction, and then we have a whole state going here. Then we have a particle state leaving, and then we have the other one particle, one whole state. So this is a diagram which also produces a two particle, two whole state. Then we can make permutations here where we have actually a whole state which would come in here. So we could actually get something which looks like this. So we just keep that one. And then we have the operator like that. And we have the two guys here like that. And then we have the interaction here, but now we have a particle state going in and not a whole state. And that means we have a whole state here. We have a whole state here, and then a particle state going out here. So again, this produces a two particle, two hole excitation. And then there's a final one, which looks even uglier. And then I'm gonna put this one here. So let me just draw this correctly. So I'm gonna have this one up here, and then I have a whole line going down here. So this is a particle line. And then I have a, let me see, I have then a particle line. Yeah, a particle line going up here. And then I have a whole line coming down. So this, here I have a particle whole pair. And then I need to have a whole line which goes down here. And then I have a particle line up here and a particle line up here. So you see now again, if I put labels to this, this could be an IJ and then an AB. So these are the diagrams which you get from this specific term. If you go to higher orders with T2 cubed, then you would get a actually a level 4, no, sorry, level 6. So here we have a level 4 with these two guys. We match it with the interaction, and that takes away one of them, and then we are left with a level 2, which is the one we want to have. So these are then the diagrams which you would get with the copper cluster with only doubles. Now, from the diagrams, you can then set up the analytical expressions, which you have to write a program for anyway. So this was a kind of repetition from what we did yesterday. And you see quickly that if you were to have something like h of n with a T2 cubed, then what you would have would be something like this. And I'm just setting up the blocks here. And I write them like particle whole states. We would then have 3 of these. So what we would have would be a 2 particle, 2 hole cubed. So which means in principle, we would have a 6 particle, 6 hole state. And this is what we would call a level 6. Now, when we match with the Hamiltonian, you see now that what we can get at most, if we have a level 2 here, or level -2, is that we would get at the end a 4 particle, 4 hole excitation. And that is not a 2 particle, 2 hole state which we want. So it means that this equation which we had when we wrote the ET2 acting on phi 0 equal to 1 plus T2 plus T2 squared divided by 2 plus T3 cubed divided cube T2. Sorry, I put the subscripts the wrong place. So this is a T2 cubed divided by 3 factorial, etc. You see now that this series actually truncates at a given order. Okay, so what I want to do now is to go back to the Jupyter notebook because I wanted to show you the equations which you can program and how you can actually set up a program for solving the equations. So let's just go back to the Jupyter notebook then. Okay, let me just do one thing here because I need to like that. So somehow when I have a full screen view, it doesn't see it when I do the screen sharing. I don't know why. Okay, so let's just do the full screen. So in the Jupyter notebook for this week, what you will find is essentially at the end here is the implementation after all the questions. A lot of these things are repetitions of what we've been discussing before. And you can see also how we can set up the ansatz for the coefficients. And a typical ansatz for the T2 equations is actually to use second order perturbation theory. So you would find, basically what you will find here is a repeat of what we have had before. So I'm not going to set that up. But the algebraic expression which you will get then is something which runs like this. So you remember that we had this term. This is a term with the one body part. So this PAB is actually a permutation where we permute particles A and B. And if you go back to the diagrams, you will see why we have to do that, because we're actually interchanging where the operator is placed. So it can be placed on the line with particle A, but it has also to be placed on the line with particle B. So this PAB is just an interchange of A and B. And the same with the hole states. And then we have the two particle intermediate states, the two hole intermediate states. And this is the particle hole intermediate state. And then we have the four beasts with the amplitudes to the power of 2. So when you use the diagram rules, which we are coming back to, then you can, from the diagrams, you can write down the analytical expressions. And these are the equations which you want to set to 0. So you want to find the roots of that equation. So when you're solving the equation then, so this is first, we have the case with the exact diagonalization, which you did in the second midterm. Now, when we then set up the code for the pairing case, this is us just setting up the different terms, which then can appear as matrix elements. So we have two particles coming in and two out, two holes and two particles, as you also had in the midterm. And then you also know that in the midterm, when you looked at the pairing model, you could not have a particle hole intermediate state. So let me just quickly remind you of that. So remember now that we could have in the pairing interaction, we could connect one pair with another one for particle states above the Fermi level. So this is just these matrix elements PPP here. Then we could excite from two holes to two particles, and that's just these matrix elements, and they are obviously they have to be Hermitian, and this is the whole piece. So these are the type of equations which we can have, because keep in mind now that copper cluster theory is set up, if you look at the equations here, with the doubles only. So you would then have amplitudes which connects two particles and two holes. Yeah.
So that, for example, is specifically for the second midterm?
Yeah. Yeah. So this is tailored to the second midterm. So the reason why I bring this up is that if you think of the final examination, and in the final examination, we want you to discuss the methods we have presented. So that means full configuration interaction theory, Hartree-Fock, a little bit DFT, many-body perturbation theory, and copper cluster theory. So one thing you could do then is that you could present the theory and then use the second midterm as an example of the applications of the theories. And then you can discuss the pros and cons. So when you think of the mean field methods, the mean field methods are like kitchen items. So you need them because they often provide a better basis suited to that specific problem. They often improve convergence. But then the methods which we are more interested in are FCI, obviously, which is exact diagonalization, many-body perturbation theory, and then copper cluster theory, which are the so-called post-mean field methods. So you see now that when you look at the interaction elements, you will see that for the pairing model, this guy here, which now connects a particle state with a whole state, has to be 0. by obvious reasons. So you will see that even for the CCD equations here, there are considerable simplifications. So the only terms which appear in the method, then obviously these terms will also disappear. You will have this one, which is a 2 particle going to 2 particle. So that will have an interaction which is non-zero. You will have a 2 particle, no, sorry, 2 hole, which goes to 2 hole. So that would be non-zero. And then when you look at these elements here, you will have 2 particles going to 2 holes. So that can be non-zero. In this case here, you will also have 2 particles going to 2 holes, and the same here, but and the same here as well. So these are elements which can be non-zero for you. This element here, which is the one which has a particle hole as an intermediate state, is obviously 0 because your interaction here is 0 by definition, if you don't break any pairs. So this makes life a little bit easier. And when we are setting up, then we need only these elements for the interaction. And here I'm just setting up the matrix elements. You see the value 0.5 times G. And then we are setting up a matrix which then contains the particle to hole hole, hole to hole hole, etc. So this just sets up what we might call the Hamiltonian matrix, because the way we run the calculations here is that everything is written in terms of matrix multiplications. So instead of performing the explicit sums here, you just, as we discussed yesterday, and I'm going to show you today, how you perform these type of multiplications, because you can rewrite everything here, this one as a matrix and this one as a matrix. And then you would perform everything, because at the end you want the indices ij and ab. So let me show you how you can do this. So let's go back to the whiteboard just for a moment, and we will come back to this when we look at the equations for singles and doubles. So let's just quickly go back to the whiteboard and look at a specific example here. So if we now look at the energy equation which we had here, so this delta E CCD, that is given by 1/4, and then there is a summation over AB IJ, and then we have the unknown amplitudes. So we have a value for these amplitudes for every iteration, and then we have the interaction matrix element, which was given by A, V, and AB here. So if you now look at the configurations which you have, so these are all the possible configurations. This is something which you would just translate into a new label. So this I here contains all two-hole configurations. Okay. Then, if I look at A and B, I just replace that one with a new label, which I call for A. And that contains simply, so that is a container which points to all the single particle states which are made up with these guys here. Contains all 2-particle configs. Now, if you look at the pairing model which we had, so let's take that as an example. That is our pairing model. In that case, what we would have is the following. When we now are thinking of low broken pairs, so we remember that we had this as the ansatz for the ground state. We call this a P equal to 1, and this a P equal to 2. This is a P equal to 3, and this is a P equal to 4. That could represent some kind of spatial degrees of freedom. And then we had a spin up and spin down. So we know that if we think of the 2-hole configurations, then there are only 2 possibilities. if you think of that. So we would have now the state 1 spin up and 1 spin down. And then you would have 2 spin up and 2 spin down. So this is us breaking it down in all the possible configurations. Okay? So that means that the total number of configs I is equal to 2. And then in our case, if we think of the particle configurations, so this was the ansatz for the ground state, but now we are looking at the matrix elements or the interaction elements. And the interaction elements deal only with the 2 particles at a time, because interaction can only couple 2 particles at a time. And that's why we break everything down to 2 particle configurations or 2 hole configurations. So if you look at the particle case, what we would have then would be something like this or something like this. So that means that we would have then for the 2 particle configurations, so let's just write 2p configs. So this is not now a many-body state, not the 4 particle state, but it is because when we break down the equations, we are breaking it down since we have chosen a single particle basis as a way to represent a many-body wave function, then we can break it down in terms of single particle states. And then everything breaks down into, although originally this was a many-body state, where we took the overlap between 2 many-body states, because the state phi 0 is actually represented by all these. But now we can make it more compact and write everything in terms of these type of configurations. And here we would have 3 spin up and 3 spin down. Obviously, this state has to be anti-symmetrized, but we are not, now we are just using a more compact labeling here. So when we are setting up the matrix elements, everything is anti-symmetrized. So that means that these states here are actually now assumed to be anti-symmetrized. So that means that the total number of configs in that specific case for the particle states, A, that is also equal to 2. So if you go back to the equation then, to this one, I can now rewrite this equation here as a matrix multiplication. So I can define a matrix T, which has indices I and J and AB. And so that means that my T, IJ, AB becomes now a matrix which I call for TIA. And that matrix is a 2 by 2 matrix because I have 2 hole configurations and 2 particle configurations. That makes sense? And then I have my interaction here, which I had as an A, B, V, I, J. And I can just rewrite that one as a V of A, I. I have 2 hole configurations and 2 particle configurations. So that's also 2 by 2 matrix. So that means that the expression which I had for the delta ECCD, that is going to be given by 1/4 times this matrix T times the matrix V. So I can calculate this in a very expedient way. Okay, so it makes sense? So if I sum over the A's, so my sum over the A's is obviously the sum here, where I sum over the A's here, but at the end, I also need the summation over the, so it's actually, if I look at this one, let's just rewrite it here. This was a little bit too compact. So the energy was 1 divided by 4, and this is ABIJ. So let's just rewrite it, EIJ, AB, and then I have this element. I can just write it like this now, IJ, AB. And this is going to be 1/4, and there's a summation over I and A. And what I have then is TIA of VAI. Okay. So this is the typical way we set it up. And when we come to the other matrix elements, we can do exactly the same thing. So let's go back to the Jupyter notebook. So you would see then that some of these quantities, like this quantity you see here with or rather like this one, this is a two-particle matrix element. This is now multiplied with the amplitude, which is a two-particle two-hole. And you see now that the summation here is something which we now can rewrite as a matrix multiplication. And then when we perform this multiplication and keep track of all the indices ij and ab, then we can simply rewrite this term here as a matrix multiplication. This is the compact way which we would use when we write the code. And essentially, this is what is done here. So we will have we are setting up the matrices. So these are the different whole matrices. And then we initialize, in this case, we have a simple Hartree-Fock matrix, which we need to set up. So we actually need, if you look back at the equations here, we actually need to pay attention to these terms as well, because we are already in a Hartree-Fock basis. So we need to set that up, and that is the term which you see here, pairing Fock. And then we have the initialization, and the initialization is simply second-order perturbation theory for all the amplitudes. So this is the way we initialize the amplitudes, by using perturbation theory for the wave operator to first order, as you did in the midterm. The only difference is that the energy denominators are given by the Hartree-Fock energies. This is exactly what you did in the midterm. Does that ring a bell? Yeah. The first order perturbation for the wave operator, because these amplitudes are actually the wave operators. So let me try to explain that a little bit. Let's go back to the whiteboard, because this is a very good question. So let's just do that so you see it more clearly. So let's just bring back, so this is also us repeating perturbation theory. So when we looked at MBPT to second order in the Rayleigh-Schrödinger perturbation theory, what we had then was a contribution to the energy was given by phi 0. We had the interaction part of the Hamiltonian. And then we had the intermediate states, which we plugged in, phi of m. Phi of m, we had this operator E0. And then we had h of I multiplied with phi 0. Now, this is something which we can rewrite as phi 0. So the interaction is to second order. But then we had the wave operator, which now is the first order, because the wave operator contains the interaction here. So that term would then be the wave operator to first order multiplied with phi 0. So that wave operator to first order, if you look at the expression for that, so this R1 is nothing but phi of m, and then we had this E0 minus En multiplied with the interaction multiplied with phi 0. This is what you compared when you diagonalized. This is actually the coefficients. So when you looked at the comparison here for the pairing model, what this was actually equal to when you did the calculation, this was equal for the pairing model, it was equal to AB Vij divided by epsilon I plus epsilon j minus epsilon A minus epsilon B. Now, your second order energy, delta E 0 to second order, was then actually equal to 1 over 4 summation AB ij. And then we had AB, no, sorry, let's just rewrite it like ij v AB. And then you had AB v ij divided by epsilon I plus epsilon j minus epsilon A minus epsilon B. Now the delta E FCI, on the other hand, with only two particle, two hole excitations, that means that you were looking at explicitly at the pairing model. You didn't have any Hartree-Fock excitations. Then that was given by one, not 1 over 4, but what you had then was a summation, and where you had to plug in these coefficients, Cij, AB, and then you had an AB of Vij. If you do now copper cluster, delta E CCD, this is equal to a summation over 1 over 4 AB ij, and then the unknown amplitudes. And this was then given by AB Vij. So I bring this up because this is a way to think of the comparison. And if you think of the final oral examination, what you could say then, you could bring up second order perturbation theory. And then you could say that, like in the second midterm, what you did then was to compare this expression with the one you got from exact diagonalization. Now, when you do copper cluster theory, when the equations have converged, you have this term here, which should be equivalent to that one. It will not be because you're summing only a partial set of contributions. But hopefully this is better than the one you had from perturbation theory. Does this make sense? So what you would do then, since you have a set of nonlinear equations in these quantities, is that you have to start the iteration with a guess. And your simplest guess is second order perturbation theory. Actually, it's first order in the wave operator. So the energy is to second order, but the wave operator is then to first order. So this is the link with the equations, which when you're making the presentation, this is a very nice way of saying, here is what I get from FCI. You diagonalize, and if you can diagonalize, you have all the beauties here. When you do copper cluster theory, you are summing only a partial set of excitations. But hopefully this partial set, which is included here, does a better job than perturbation theory order by order. Okay. So if we then go back here and look at the code, this is where we stopped. This is actually second order perturbation theory, which is coded in here. And then this is the iteration. And in the iteration, we start with a guess. And we set up all these different terms, the intermediates, so the different diagrams. This is actually refers to a book which I wrote some years ago. So I can give you the link to that book. So these are the equations in the textbook. And it essentially sets up the copper cluster equations, which are those which you see here. These are those which are used to set up the amplitudes. So it's essentially us going through that. And then the energy is now simply, so we have the Einstein summation here, and we have simply the multiplications of the amplitudes with the T2 with the interaction. So we have a particle hole, which is just minus 1/2 times g, as in the midterm, and multiplied with the new amplitudes. And in this case here, I just put the number of particles to 4, the number of levels to 4, exactly as you had in the midterm. But this is something you can change as you want. And here I just looked at g equal to 1. And then I initialize everything. I have the Fock, the single particle energies. I initialize the T2 amplitudes. I get a new energy. And then I have the iterative process. And this does 60 iterations. So this is solved iteratively. And you can see now that it converges not so badly. So if you look at now at the convergence at the level of the 10th digit, you're roughly at that level after 60 iterations. And then in the beginning here, you will also see what you get with many-body perturbation theory. And this is also compared to, this is the initial one when you have, and this is the many-body perturbation theory. So this is just to check that you get the same. And then there should be, if you now run the, if we go back and we run the exact diagonalization, you see now that the last point is 3.644. And if we go down here, it's not that bad. So the exact one is 3.644 and we have 3.695. Now, copper cluster theory is non-variational, so we can converge from below. Okay? So this is, if you look at the equations we put up on the whiteboard, these are the type of comparisons you can bring up when you discuss these things during the midterm. If this is what you want to do, I mean, people have actually, sometimes we have people who actually work with copper cluster theory for their master thesis, and they have picked other types of examples as well. So what we will do after the break is actually to jump into these slides. And the reason you don't find these in the Jupyter notebook is simply because all the wick contractions cannot be rendered by MathJax. So I have to use a mix of standard LaTeX slides and also the Jupyter notebook here. Okay, should take a small break. I went a little bit over time, so let's do 15 minutes. That's okay. And be back at 11:20. So what I want to do now is to give you a kind of, in a way, rushed approach to the singles and doubles, which is normally called CCSD. So that means that instead of just taking the T2, which we did till now, so if you have understood how we derive the equations, what comes in now is an additional complication. So we simply get more terms to have to deal with when we set up the iterative solver. But if you've gotten the basic concepts with the T2, then this is just an additional complication. So I will step you through, one, the diagrammatic approach, and two, all the equations which we can set up in order to get the final expressions. And then the expressions you end up coding are essentially those which are lookalikes of what we did with T2 only, except that now you have to have a one particle, one hole operator as well, a T1 operator. Okay, so I'm going to just use the slides. And one of the things I quickly wanted to remind you of is, and this serves also as a reminder, because we deal normally with a normal ordered Hamiltonian. And in our case, we have the one body operator and the two body operator, if we stay with that. And you will also see the kind of notations which you find in, let's say, the textbooks. So what I did here was to borrow some of the notation from Shavit and Bartlett. So this is just to link what we have done with that textbook, which has become a kind of standard textbook for those who do quantum chemistry in many-body theory. And you will often see a notation like this one. If you look at this one, that stands simply for the anti-symmetrized two-body integrals. So we skip all the AS. We assume now that these are anti-symmetrized operators. Now, if you look at this H of n, what you typically do then, and this is just a repeat of what we did. So we contract H of n with 0, 1, or multiple T elements. So for the T2 amplitudes, we had the T2 squared with the operator H of n. Then at least all these elements, and we saw that from practicing, that they must have at least one contraction with H of n, and no contractions between the T elements are allowed. And a single T element can contract with a single element of Hn in different ways. So if you now look at the diagram rules, so we have particle lines. So that represents a contraction between second quantized operators. External lines are connected to one operator vertex in infinity. Internal lines are connected to operator vertices in both ends. This is just a repeat of what we have seen before. And then we introduce this naming where we look at the particle hole excitations. So horizontal dashed lines segment with one vertex, like this one, and excitation level identify the number of particle hole pairs created by the operator. So this is basically what we did yesterday. And then when we look at the two-body Hamiltonian, we had these different contributions. Keep in mind also that here we don't list the exchange part. So when you look at an element like this one, there will also be an exchange part, which is assumed that it has to be there. So normally when you set up these, if you look at these integrals, which you have here, and you write them as diagrams, typically what is done is that you only write one of them. But this one contains both the direct term and the exchange term. But when you draw the diagrams, you just leave out one of them. And that means that here we just draw this one without the exchange term. And similarly here, this has an exchange term where you have one particle coming in and one out, and one hole coming in here and one hole going out there, which is not drawn here. And these are the different types of excitations we can have. So this is a one particle, one hole, one particle, one hole. Actually, this is normally called a free particle, one hole, because you have three particle lines and one hole. This is a free hole, one particle. This is a two particle, two hole excitation, and this is a two particle, two hole de-excitation. And then we have the operators. So the operators create a one particle, one hole pair. So this is a level one. And then this is a level two. This is basically just a summary of what we did yesterday, what we discussed. And then when you look at the calculations, so this is you will also see this notation. I hate this notation, but I actually brought it back because it's, I shouldn't say hate. I don't hate. I mean, I dislike. That's a better word. But this is a notation you will often see in quantum chemistry. And I've kept it because we've been using the Shavit and Bartlett textbook. So in this case, you have no external lines. You just end with zero particle, zero hole, and you start with a zero particle, zero hole. And the final excitation level is zero. And then you can bring in the different blocks here. And then you know that the T operator has the either one particle, one hole, two particle, two hole. And these are the interaction terms which you have. I mean, the first line is the one-body operator, and the second one is the two-body operator. And then we simply have to bring these together and get the right excitation level. So you can think of these as Lego building blocks, which you just put together. And then this is what you get. If you do T1 and T2. Now, in our case, we did not have T1. So the only one which we got was actually this one. But this is a contribution to the energy. And then when you have these diagrams, you can write down the analytical expressions by using the diagram rules. And these are the ones which you have to code anyway. So when you then look at the diagram rules, so we have label all lines, sum over all internal indices, which means all internal particle and hole lines between vertices. You extract the matrix elements. You have this one out, in, and then you have left out, right in, out, left in, right in. And then you extract the couple cluster, or the cluster amplitudes with indices in the order left to right, like you do with interactions. So you have out and in, left out, right out, left in, right in. Then you calculate the phase factor. And now in this case, there is no energy denominator because the energy denominator is actually included in the amplitudes. If you think back to what we put up before the break about the energy to second order in the interaction from perturbation theory. And then you have the factor of 1/2 for each equivalent line and each equivalent vertex. So if you use that, this is what you get for the energy. And now we are using the Einstein summation in this, Einstein summation here. So that means that these equations here, it entails an implicit sum over repeated indices. Are you familiar with that type? Yeah. Okay. It's almost an offense to ask about that. Okay. So that's a very compact way of writing it. And you see now this is the one we had when we only had CCD. But then when we have the T1, we get 2 additional terms. Now, if we have performed a Hartree-Fock calculation, then this term here, which links a whole state with a particle state, is 0. So if you're dealing with a Hartree-Fock basis, then some of these are actually 0 by definition. So that means that if you have a Hartree-Fock basis, it does not mean that these guys disappear, but you have 1 term less here. Does that make sense? Then we get the next equation. So when we write the equations, what we are doing now, we've shuffled over to the left-hand side all the terms so that we actually have 0. And then we have we are taking the second row of the Hamiltonian matrix, we multiply with a 1 particle, 1 whole state, and then we have all the junk in between, as we did when we derived the FCI equations in the clumsy way. So we have to end in a 1 particle, 1 whole state. That means that the final excitation level is +1, and that means that it has to look something like this. So there's a black box which contains all the things we have been iterating on, all the types of correlations which we're summing to infinite order. And then we simply have to match the elements here, the T's with these ones. And when we do that, we get the following diagrams. So we are simply taking then the different possibilities which we have when we link these operators. And since we require that the final excitation level has to be +1, you see that there is a natural truncation here, because this one has an excitation level +1, +1, +1. That creates a 3 particle, 3 whole state. But you have to end with a 1 particle, 1 whole state. So later we are going to see how this comes through when you do the algebraic expansion. Now we are simply putting together diagrams with different excitation levels. And then we can see immediately from that it has to stop somewhere. Because if you think of the operator T1, when you Taylor expand that one, there should be a T1 to the power of 4, T1 to the power of 5, etc. But since we require then that this should at most be a 1 particle, 1 whole state, and we have a 2-body interaction only, then this has to stop at the level of T1 cubed. And then when you have all the diagrams and you assured yourself that these are the only ones which appear, then you can start setting up the analytical expressions. So when you do this the first time, it's always useful to do both diagrams and the algebraic calculations. And then again, the diagram rules are exactly the same as before, as we have seen them, except that now we don't need to deal with energy denominators because they are baked into the amplitudes. So just keep in mind that the amplitudes are dimensionless. And this is what the equations are going to look like for the T1 amplitudes, when you then take the diagram rules and you set up the equations. And this is still Einstein summations. And that's why you see for many of these sums, it can also be convenient to calculate what we call intermediates, because if you now are doing all these multiplications, you can actually pre-calculate some of the terms. And I will show you later how you can do that. So then the next one is a T2. And in that case, we have to end with a 2 particle, 2 whole state. These are the 2 guys which can contribute to the wave operator. And these are the elements in the Hamiltonian. And then you have to put these together, and then you get many more here. And you see now that the term which you have here, for instance, this is a T1 to the power of 4, because T1 to the power of 4 gives us a 4-particle 4-hole state. Then we have the interaction, which you see here, and that's a 2-body one. And that if we have a excitation level of +4, we need to have a 2-body interaction with an excitation level of -2, which then brings us to a 2-particle 2-hole state. So by setting up all these types of contributions, this is what you end up with. Now, anything you see here now is something you can generate automatically if you use, let's say, symbolic Python. And then you can figure out what the different contributions look like. But it's always a useful exercise when you do this the first time to do it both diagrammatically and algebraically. Again, this is what you do. The same diagram rules, I just repeat them here for the sake of completeness. And then when you set up the diagram rules, this is the equation you get. And now it looks much uglier because you're mixing T1 excitations with T2 excitations. So you would have terms here which contain both T2. So this is a T2, that's a 2-particle 2-hole. This is a 1-particle 1-hole. So this is a 4-particle 4-hole, which is then joined with a 2-body interaction and brings it to a 2-particle 2-hole excitation. So these are the equations you get if you look at the diagrams or if you then do it algebraically. So the expansion, which we typically have when we use the Baker-Campbell-Hausdorff expansion, is a set of nested commutators. The problem is that, no, not the problem, the benefit of doing it like this is that these nested commutators, they stop at a specific order. And just keep in mind now that if you have a 2-body interaction, this is the terms which go like T1 to the power of 4 would appear here from this term. And then you have the interaction. So then you get T1 to the power of 4 times an interaction, which then can lower it down to a 2-particle 2-hole excitation. So that means that this summation here truncates exactly at a given order, which is defined by the interaction you have. So if you have a 2-body interaction, the nested commutators, when you expand everything, they terminate at the order of 4 nested commutators, which is what you see here. So the energy terminates at an earlier stage. So if you then set up the energy, you would have terms which look like these. So this would be with the T1 and the 1-body and T2, 2-body and T1, and 2-body and T2. And then you need to set up the different commutators. And what I have here is a set of examples of the way you would proceed in finding these expressions. So I can see this, there's a lot of excitement in seeing all these terms. I'm just putting them here for the sake of completeness, because then you get terms which look like these. And if you then go back to the expressions which we had, you will identify some of them as the final diagrams. So I just put them up for the sake of completeness. I'm not going to go through everything here. But I just put up, so this is a kind of label you would have to do in order to find the expressions. So when you do the 2-body operator with the and the 1-body one, and you are on a Hartree-Fock basis, this is the terms which you get. If you are on a Hartree-Fock basis, which is the one we could write off immediately from the diagrams. And this is what you would get from the algebraic contributions. And then you can continue. You have a T2 term here, T squared. And in that case, what you would get, if you now don't, if you remember back to the diagrams which we put up, I did say Hartree-Fock basis. This is irrespective of a Hartree-Fock basis. So if we look at the energy was given by these terms, this one and this one plus this one. So this term comes from actually the, if you now look at the commutators here, so let me just go back again. So when I look at the energy, the first one is something which when we set everything together, we got this term, which was the first diagram with the one body operator, which you have here. This is the two body operator. And then we have a term with a t squared. And the only term which contributes, because t squared here with a two body operator would give a 4-particle 4-hole. And the interaction then would at most give us reduce it to 2-particle 2-hole. So the only term which then can contribute is the one with the T1 amplitudes. And that was the third diagram which we had there. So when you run through everything in an algebraic way and do all the possible contractions, this is, it's not an exciting exercise, but it's actually good to do it if you want to convince yourself about the final equations. So what you find in the slides here is essentially the way you would derive all these different equations, term by term. I can see the excitement here. But I just wanted to bring it up for the sake of completeness. Okay. And then no contractions are possible between cluster operators, and cluster operators need to contract with 3 indices to the left. Disconnected parts automatically cancel. All one-body operators can connect to maximum 2 cluster operators, and two-body can connect to maximum 4 cluster operators. And different terms in expansion contribute obviously different equations. So one of the things you can do is actually to factor specific terms. So if you now want to calculate, and this is now given in the Einstein summation notation, you're just summing of all these indices. If you look at these diagrams, they're actually diagrams which you, or contributions which you can pre-calculate. So this is called a factoring. And what you could do then, if you look at this term here, is that you can calculate that as an intermediate, which you call x here. And then you can simply set this up as expedient matrix multiplications. So some of these factors are factors you can pre-calculate and then insert again in other terms as well. And that saves a lot of CPU cycles if you can pre-factor things and then pre-calculate. So factoring the examples here on how you can do that. So if you look at this expression here, you can actually rewrite that in terms of this one. But then you can also multiply this t IE together with that one and define a new one here, because these are repeated summations. And there are just some examples of refactoring here, which can be done. And then you would reuse. So this would be a typical diagram which appears in the 2-particle 2-hole amplitudes. And this is a diagram which you can refactor here. Okay, I'm not going to go through all these things here. So basically the algorithm, if we set it up, you would set up a model space with the single particle states. You would calculate the V and the V amplitudes. You can store them. You initialize these amplitudes. And then you have an algorithm where you simply keep updating the terms. So while it's not converged, like you saw with this program for the CCD equations, you set up a convergence criterion. You calculate the intermediate values. You update the amplitudes. Then you calculate the new energy. And the new energy would then be simply given by the new amplitudes multiplied with these elements which you have stored once and for all. And then you continue till this convergence criteria has been reached. And that's the standard Hartree-Fock recipe. And it's a kind of lookalike of what you had with the Hartree-Fock recipe. Okay. So this was essentially the last thing I wanted to say in connection with this course. And then we could discuss a little bit the final exam if you want to. The thing which we want you to do is to have a presentation of roughly 25, 30 minutes. So you have to prepare slides. Don't use the Blackboard. Have slides prepared, because if you use the Blackboard, you will barely get anywhere. So you need to have prepared slides. And then you should cover the methods we have discussed, which means basically, so if we switch back to the whiteboard, so let's just set up the elements which you should have in your presentation. So if you look at the final oral examination, these are just bullet points, and in case you are in doubt, I mean, please just send me an email. So the presentation should be roughly 25 to 30 minutes. And then we have 10 to 15 minutes for questions. There is an external examiner as well, obviously, because we have to be two when we grade. What it should contain, your presentation, you can, many people like to start with a second quantization and present that. Wick's theorem, briefly. I mean, you don't need to make tons of slides about that. So we call this just a background. So that would be second quantization. Essentially, that is the anti-commutators. And the basic operations you do. We have only focused on fermions. So, but if you want to add something about bosons, you can do that, but it's not required. And then you would have Wick's theorem. And the generalized Wick theorem is important. You don't need to prove that, but you should state it. And then you have some of the background. Obviously, the background also contains things like you using an orthogonal normalized basis. That's your computational basis. So these are all the kind of small petit ingredients which then form the background. And that could typically be 1 or 2 slides at most. And then we have the methods which we have covered. So we have FCI, obviously. And then we have the Hartree-Fock plus DFT. You don't need to say so much about DFT. You can if you want to. If you want to digress a little bit, you can do that as well. And then we have many-body perturbation theory. And then we have copper cluster theory. So these are the, the 5 many-body methods. And then you can choose to link with actual calculations, where you demonstrate some of the methods. So here you could take the, let's say, the second midterm, or if you want to stay with the Lipkin model, you can actually do that. You can take a simplified Lipkin model, because you remember the Hamiltonian had a 2-particle, 2-hole, and a 1-particle, 1-hole part. So if you look at the code which you have for the copper cluster theory, you could actually do CC on the Lipkin model. You could do many-body perturbation theory on the Lipkin model. Actually, the Lipkin model is fantastic. You can use it to study phase transitions, critical phenomena. I've been using that when I do quantum computing. You can study entanglement, all different measures. You can do time evolution on it, etc., etc. It's a very well-studied model. So you could then link, when you say link with calculations, that could be the second midterm. You could take the pairing model, which contains some of the basic correlations, like the 2-particle, 2-hole ones, which you can produce with many-body perturbation theory and copper cluster theory. When you diagonalize exactly, you obviously get all the correlations. So these are essentially the things we want you to discuss, obviously with a critical view. So if you think of the second midterm where you looked at many-body perturbation theory, if you now stretch the result from -1 to +1 and you let the interaction strength be stronger, you will see larger and larger deviations. And that's something which is always nice to show, because then you can see that, hey, we expect that this should happen, but you can clearly see that it breaks down. And then you need to do perturbation theory to infinite order to to sum up all the contributions. So pros and cons, be critical, and then at the end you should have some conclusions, discussions of pros and cons, and some conclusions. Yeah.
How much detail should we go into for the methods of the duration of the equation itself?
You don't need to go.
Or...
No, it should be more. You should, if you think 25, 30 minutes, that is 20 slides roughly. So that means that you don't go that much into the details, but what is convenient when you make a presentation is to have backup slides. So the thing which is, I guess that most of you have some kind of LaTeX slides, which you had for the midterms. That means that you have coded the equations, and then you can, if you want to, I can send you also, but I guess everybody has. How many of you have written slides in LaTeX? That's okay. I can provide you with, there's a LaTeX style, which is called Beamer, which is very nice to make slides with. And then you also have access to all my notes. Keep that in mind. So if you look at, actually, I don't need to send anything to you because you have access to all the material. So if you look at the, let's just go back to the Jupyter notebook here. So if you go into the doc folder, you will find examples of, so if you go to SRC, which stands for source, and you go, for instance, to week 47, there is something which is called LaTeX slides. And this contains, the slides which you saw now on copper cluster theory. So, and there you will see all the lovely contractions. Actually, this took me a horrible amount of time, really a horrible amount of time. Now you can generate everything with ChatGPT like this.
Just as much as
Actually, those slides you saw now, that was some weeks of labor, which you can just generate in a few seconds. It's, yeah. I won't say anything about that. But you have all, yeah.
It's sufficient just to present the equations without sort of deriving the whole minimization.
Yeah.
Here's the equation, here's the results.
But you can have backup slides in case you you want to have more. And if you are in doubt, I mean, you can always just ask questions. Sorry. So if we go back to the anyway, you have lots of all the slides, all the source files are actually there. So if you want to use it, feel free to do so. I actually would be very happy if you reuse it, because then I've done something meaningful and useful. But this is roughly the kind of layout for the presentation. And then we would have some 10, 15 minutes where we can go back and we may ask questions. And then typically we switch between the blackboard and so on. Or if you want to write on pen and paper, you can do that as well.
Sort of the typical blackboard.
Yeah.
What would be a typical sort of exercise that you have to do on the blackboard?
Oh no, it's more from a we're not going to ask you to derive equations on the blackboard, because that can easily take a lot of time. But it's more the kind of overarching understanding of what you're doing. So it could be, let's say, I could ask you, how is the Pauli principle encoded in second quantization? That would be because the way you would do it in the standard way is to set up, let's say, an anti-symmetrized answers for the wave function, which you could do with a Slater determinant. And then the question is, how do you represent that in second quantization or in what we call Fock space? And the answer to that one is pretty simple, because the anti-commutation rules give you the anti-symmetry. So these are more the kind of conceptual questions. I would say that I normally prefer that. I normally never ask for explicit details, because that can easily go off on a tangent, and people never finish, because some people get very nervous, and yeah, there's more conceptual ones. Well, conceptual ones about Hartree-Fock. If you think of density functional theory, there's a lot of conceptual stuff in density functional theory. And then clearly, like the differences between many-body, if you look at a typical example on the differences between many-body perturbation theory, FCI, and copper cluster theory, there are different ways of finding the amplitudes, which you would get by exact diagonalization, if you can diagonalize. And then you have approximations. So this is also kind of more, how to say, conceptual question, actually. What are the differences? This is also something you can have in the slides. Oh, yeah. Yeah, no, any of the Scandinavian languages, so we can have, yeah. You want to have it in? Yeah. It depends on the external examiner, which we have here. Yeah. Feel free to ask questions. So I will send you a mail with suggested times. And the first iteration will just be Monday the 15th and the 16th, but with the 19th as a backup. But the QFT people will probably like to have it on the 15th, as early as possible. More questions? Okay. Yeah, I think I don't have much more to say. I mean, you've been very patient and listened for 15 weeks times 4, 60 hours. Thanks, guys. Thanks for coming. And enjoy your time, and best wishes. Thanks.
Service.